Howdy!
My name is Ethan Andrews.
My name is Jonathan Bowie.
My name is Nathan Figueroa.
And our project for this year's MXET 375 course was the Quadruple Pendulum.
The team folder link located above is where you can find all of our data, all of our extra sheets, and anything you want to know about the project.
So, for our project, we were inspired by the simple pendulum and the double pendulum, but we wanted to make it a little bit more complicated as we thought we could do that in the time frame. So the double pendulum can only get so complicated, therefore we wanted to double the amount of degrees of freedom and components to create the quadruple pendulum and take it as far as we really could within the time frame we had. For our project, we wanted to construct a functional quadruple pendulum with 4 degrees of freedom and simulate that pendulum to obtain the data. And as well, when we run a legitimate experiment with the pendulum, we wanted to motion track the 4 different bearings and see the pendulum's motion in itself to obtain the data there, comparing it between the theoretical and the experimental data to refine it through a parameter estimation and have an accurate simulation through Simulink. Located above are the 3 concept views of the project. I created them in CAD myself. They show the 4 descending pieces of the pendulum that are different sizes so that they can fully rotate all 4 of them, and the spaces in between them so that they do not collide with each other. Our plan was simple on the mechanical side. I was going to 3D print a rough estimate of the pendulum design, refine that pendulum, and print it one more time. We were going to build a frame out of wood, construct that frame, put a green tarp over it so we could have a nice clear background to track the pendulum's motion, and assemble the pendulum onto the frame. On the simulation side, Ethan created a block diagram for the pendulum, imported my 3D model design, and took the recorded pendulum motion from our experimental drop and approximated the parameter values based on the video we sent him. We then used a video tracker to get that data, and he implemented the data into the simulation to further refine the parameters in the parameter estimation.
So for the simulation design, as shown on the slides, I took the idea from our lab 5, the kind of like the importing CAD models lab, where we did a test of the simple pendulum, and just like we took a simple pendulum and made it more in a quadruple pendulum. I did the exact same thing for the design process of it. So I created 4 subsystems. Within each subsystem, I have the subsystem of the first rod displayed, showing rigid transforms, revolute blocks, and the file solids for not only the pendulum rod, but the bearing for each pendulum, so that I could have that additional weight that would be located at the tip of the pendulum. So as shown in the functional block diagram, I have those 4 subsystems with the proper icon image of the pendulum rods to indicate each and every stacked pendulum for the quadruple pendulum. Following the output of each of these subsystems is the X and Y graphs for all 4 of them, alongside 2 scope outputs to then output the angular position and angular velocity of the simulated quadruple pendulum, which we will compare within the X and Y graphs, the position, the angular position, and the angular velocity of the physical model. For the subsystems of each one, nothing was different about each one besides general angle placement to match the physical model, but the file solids were just the imported CAD files that Jonathan created, and each one was of varying size. So I just had to make sure I imported the CAD models properly, adjusted the weight accordingly. So each of the CAD models each had like a separate weight due to their differences in size, but all the bearings held the same weight since the bearings that we used were relatively constant. Other than that, that would be it for the overall design of the simulation in regard to creating it and outputting both the X and Y graphs, which are indicated in the slide, and then of course the scope outputs as mentioned.
So for the mechanical design, we had many rough drafts of a frame. Eventually we settled on the design of a wooden exterior with a beam in the middle and some sort of canvas laid over the front, and a hole drilled through the back of that beam to have a screw placed through with the pendulum on the other side. From the end of that screw, the pendulum would be attached on, and dropping down in a cascading order, as so much as a ladder, the pendulums were assembled and color coordinating stickers were added onto them for motion tracking. We had 4 different lengths of our total pendulums. We had a 210 millimeter, a 180 millimeter, a 150 millimeter, and a 120 millimeter. The shortest one being at the bottom, we wanted to have the most erratic motion possible because the lengths of the other ones would generate a lot more momentum and motion, causing the smaller bottom one to spin a lot faster and a lot more frequently. On the right, we have our initial frame schematic, which was drawn up by Nathan after a couple introductory and thought process designs. And we used those measurements, we took some wood, we cut it up, and we created the frame that you'll see above.
For the mathematical model, we looked at every piece individually along the pendulum and went arm by arm. And we went in and found the equation of motion for the first arm, then the second arm, then the third, and the fourth consequently. First arm, as you can see, is pivoting around the top point. So we took the forces as it would be from the center of mass, since there's 2 bearings on both sides, center of mass would be in the middle. We also put the reaction force of the second pendulum arm reacting on the bottom into the equation and accounted for that. On the second, we accounted for the reverse forces from the first, back onto the second, went back into the middle moment of inertia of the second arm, and then accounted for the third arm's forces onto the second arm. Then for the third arm, we repeated the same process as the second arm, as both arms were linked in the same manner, but as of different lengths, they would have different moments and thus different equations to connect them. With the fourth arm, all that is holding it up is the rotation about its point on the end of the third arm pendulum and the movement as it reacts to its moment of inertia and weight of gravity pulling it around. For the experimental results, we use a tracking software, open access online. We went in and manually looked at some tracking components and where the automatic tracking had failed, and we came up with some charts for the XY components along with charts of the velocities of each arm, as you can see. There is a very sporadic motion at the beginning with the decrease in noise of the velocity, and then it becomes a very much more sinusoidal motion and much more oscillated type motion.
In comparison to the physical data that we just showed, we also, as represented in the slide, is the angular position and the angular velocity post parameter estimation of the simulated results. So after I ran the parameter estimation and got the more exact damping coefficients, I just reran the simulation, reran the overall run of it, and then got the data for the position of each and every rod from the top to the bottom. So it's 1 through 4, looking at the top, so the blue line being the first one, for both the angular position and velocity. The sporadic motion is a little more compressed due to the run time that I displayed it on. However, it does mimic the idea of more sporadic motion initially and then kind of simmering down or going down into a more oscillating motion, like the sinusoidal motion for both the angular position as demonstrated in the previous slide on the upper graph, and then the angular velocity being more kind of flatline, smaller oscillating waves towards the end. Also displayed on this slide, I have the approximated damping coefficients, which were each coefficient was set by a variable for each of the revolute joints in the simulated design. And when I did the parameter estimation, I just estimated for each of those coefficients. So the top image was the approximated one, the bottom image is the parameter estimation damping coefficients, which also shows that I was pretty close on approximating the damping coefficients, and it only ran through 4 iterations, and it was a 2-minute parameter, not even a 2-minute parameter estimation. So it's pretty solid approximation on my end.
Our experimental video and the simulation videos are located at the links above.
They will also be demonstrated towards the end of this video.
So for our project as a whole, we were able to successfully construct the pendulum that we initially thought up. Through a couple different iterations and a couple different changes. We started with a more rustic pendulum that was straight rectangular. We ended up switching to a circular-ended design, and we ended up getting the motion that we initially wanted when we set out to start this project.
The mathematical model went through a few phases of trying to figure out where and when to apply certain techniques, such as when to apply translational motion on the reactive forces, or when to try and apply rotational motion based on the arm swing. But when we went through revision and went through a few aspects that we had considered before, we came about with the equations we have now and believe these are the accurate equations of the pendulum we have.
And the simulation does closely mimic the experiment in its actual run and also in the gathered data.
The visual tracking for the data was successful. We were able to take the video of our actual experiment and convert it to the data, and it was able to work flawlessly within the simulation.
There was a successful parameter estimation, as I mentioned previously, with the lower amount of iterations and the exact damping coefficients to achieve the closely mimicked experiment. And we did acquire the appropriate parameters, which were purely just the damping coefficients, as we are dealing with a pendulum.
The behavior of the pendulum that we had desired to output, which was an erratic and sporadic behavior, had come about with our pendulum in experiment and in simulation, as they both closely relate to each other, and we have achieved this aspect of our lab.
And to finalize the actual motion that we mentioned that we wanted to kind of track, it would go into the X and Y graphs. And this is just to like add on to previously mentioned motion, like in regards to angular position and velocity. This will mimic the X and Y position of each and every rod. So each of the physical motions, generally the positions between both of the physical and simulated models are displayed above. And each of the rod pendulum is attempting to reach a full circle. That's the whole point of the sporadic motion. So the X and Y graphs kind of pinpoint the certain iterations as each pendulum rotates. And some of the X and Y graphs, like as shown above, especially in the physical model, are a little more sporadic, showing that the pendulum was erratic in its behavior. And the graphs kind of depict their placement in relation to each of the rod swings, as shown above.
The references that we have found for the pictures and the slides, as long as outside sources, can be seen in this reference slide.
For our distribution of work, it's very similar to our proposal. We see this as a very large combined group effort. No one was alone in any portion of their project. Ethan was the head of the simulation, parameter estimation, and the experimental simulation comparison. I took charge of the construction of the model itself, designing it, 3D printing it, designing the frame, different construction of the actual model itself. And Nathan was responsible for the theoretical behind it, so the visual motion capture, the mathematical models, and the equations of motion, and as well assisting me in the model construction with the construction of the frame.
And for how the work was kind of split, of course, we split into three kind of ideal tasks, whether it be design, construction, and execution. And following the timeline as shown in the Gantt chart, everything was kind of approximated as like that's how a Gantt chart is to work. So not every deadline was generally met. Some days we were either done earlier or we went a little bit over, but in the end the project did get completed, and that's what really matters. Everybody followed their general tasks as mentioned before in the kind of distribution of work, which also followed alongside the timeline.
Thank you very much. We had a lot of fun creating this project, and we look forward to proceeding further down the line.
Thanks, Ngego.
Thanks, Ngego.
Push the gears, make circuits dance, building futures with our hands, blueprints hum with dreams we weave, innovation's what we believe. Wires spark and motors spin, control the chaos deep within. Electronics is our light, guiding stars through the night. We are MXET, Texas A&M's legacy. Robots rise, futures ignite, engineering dreams take flight. Push the gears, make circuits dance, building futures with